So just to remind you, before 11:59 on Monday is when you need to submit that design project. And it has three main parts to it. We went over the assignment a little bit in class last time. And the culvert analysis and culvert design that we're going to do today, I think will just familiarize you a little bit more with how to use HY8 and how to think about you need to think in 3D for these culverts. So that's the purpose of these. And then the class on Monday of next week is going to be online. That'll be a recorded video rather than a face-to-face meeting. Okay, so here's the first of the two examples that we're going to look at today. We're going to begin with a specified culvert geometry. This is a box culvert, which is 1.5 meters by 1.5 meters. We're given the material roughness of the culvert, and then the channel is a different material downstream of it. What we're going to assume is that the channel and the culvert have the same slope. And so you can see we're identifying the invert, which is the bottom of the culvert. The invert matches the stream upstream, and the invert of the culvert also matches the tailwater channel. So what we're going to have to do is ourselves calculate what are the elevations in order to make that true. You know, the example that we worked through in class on Monday, it was kind of given exactly as we needed to enter it into the program, where, you know, the invert elevation was specified upstream and downstream, the inlet station was specified upstream and downstream, but sometimes you may not have like a preset station system, and you may not actually even know the elevation of something, but you may be able to infer the slope of the culvert, because, you know, if the culvert matches the channel slope, and you can determine the channel slope with WMS, for example, it'll tell you the slope of the channel, or you could maybe have known the slope of the channel using elevation data through Google Earth Pro or LiDAR data. But there may be situations where you don't necessarily know the absolute elevation of things, and so you have to basically just assign one. So you're going to say, for example, let's just call the invert elevation upstream 100. And let me write this on the board for us to keep track of as we go through entering this into HY8. If we say let's have the invert upstream be 100 meters, then if as a 0.007 slope and the culvert is 40 meters long, then what should this elevation be? Okay, so it should be 100 meters minus 0.007 times the length of the culvert, which is 40. And so over the course of 40 meters of horizontal length, the elevation that we're going to be losing is 0.007 times that. So 0.28. So it's 100 meters minus 0.28 meters. And so 99.72, right? 99.72 is going to be the elevation of the downstream invert. Okay, so there's two main things we're going to try to determine as we work through this together. First of all, what flow water causes the headwater to rise up to the 2 meters that's described here, with the channel width being 5 meters downstream. So it's a rectangular channel downstream. So here in the tailwater, it's a rectangular channel. We're going to have to put that in. The width is 5 meters, rectangular in shape. The slope of the tailwater is the same as the slope of the culvert, 0.007, because it's matching. They don't necessarily have to be matching, but basically what we've done is we've taken a natural channel and we've just laid this box culvert down on top of the natural channel. So the slope of the culvert matches the channel slope. Okay, so that's going to be the part A. And then if we were going to change the width of the channel, then how wide would the channel need to be for the depth to be 2 meters for the flow rate that we determined in part A? Okay, so part A is basically find Q for headwater elevation is equal to 2 meters. So if we say that this is 100 meters, what we're looking for is, here's a 1.5 meter culvert opening, and so the water's going to be up here. The water's going to be an extra 0.5 meters above the crown of the culvert, but not yet overtopping. We don't know the elevation of the roadway surface. That's not specified. We have to put something into the program because the program's going to be asking, well, like, it's on the lookout for overtopping. In neither of these parts is there overtopping. So, I mean, we could make the roadway elevation like 2,000 meters. It doesn't matter. We have to put something in, but we want it to be more than, you know, we're going to drive the headwater up to 2 meters. So this elevation is going to be 102. So let's just say that the roadway surface is at 103 meters. And then if we see overtopping, then we know that the flow rate is higher than the one that we're looking for. We're looking for what flow rate causes the headwater to rise up 2 meters. So that, anybody have questions about the setup for part A? Okay, so let's go through it together. I gave you the handout so you can see the questions and the givens and everything as we work through it. So in HY8, we're working in SI units again on this example, and it defaults into customary, so I need to close this and switch over to SI units. And then culvert, new culvert crossing. Okay, so we just want to double check that the units here where it says CMS, that means cubic meters per second. Okay, now the question is asking what flow rate causes the headwater to rise to a certain height. We don't know. So we're just going to have to put in a design flow and see if that goes high enough or maybe it's too high. It's going to be an iterative process. So let's set the design flow equal to 8 cubic meters per second and the maximum flow equal to 10. And I honestly don't remember what the answer to this one is, so we may have to go back and change that later. Okay, so you'll remember that the first thing it's asking about is the tailwater. We do have a rectangular channel with a bottom width equal to 5 meters. Channel slope is defined as 0.007. 0.007. And if you look to the right here, it reminds us that this is as a fraction, not as a percentage. So one of my favorite tricks on exams is to tell you the slope in percentage and see if you remember to convert it over to like a fraction if you're putting it into Manning's equation. Same thing here. They're just letting you know that the slope you should put here is not as a percent but as a fraction. So 0.007. Okay, Manning's end of the channel, the handout told us that the roughness of the channel was 0.05. And then the channel invert elevation is going to be the same as the outlet invert elevation of the culvert. So it matches up at 99.72. Okay, we just take a look at the rating curve here, and it tells us certain flow rates and how deep the water is. So, all right, that doesn't really answer anything for us yet in terms of what it's asking in part A. We want to find out the headwater. So we still have more that we have to tell it about the culvert. First of all, the roadway is at an elevation of 103, but where here it's asking about the stations of the roadway, this is the station description doesn't actually define anything from our hydraulic calculations. It's just so that we can know which culvert we're talking about. So I'm just going to leave that blank for the first roadway station. Crest length is asking about, like, if you're crossing, remember, a 5-meter channel, this is the front view. And here's our concrete box culvert is 1.5 meters tall and 1.5 meters wide. So if the water's going over the road, then probably it would flow over the road at more than just the width of the culvert. It would flow over the road if the water continues to rise the entire width of the channel. So let's just say that the crest length is 5 meters. It doesn't matter, by the way, for our hydraulic calculations, because nothing that we're trying to find out involves overtopping. So we could say the crest length is 5 meters or 5,000 meters. How long the crest is depends on how high over the culvert the water has to get for a certain flow rate above what's going through the culvert. So we'll put crest length equal to 5 because that's the width of the channel, but that doesn't matter. The crest elevation is important. We just have to put that higher than the 102 elevation that we want the water to get up to. So I'll put 103 for the crest elevation. And then the top width, if this is a 2-lane road, then the top width might be 8 meters. Again, it's not going to matter because the overtopping component of the flow isn't what we're trying to understand. It's just how high the headwater gets prior to overtopping, what flow rate causes the headwater depth of 2 meters. All right, so our one culvert that we've got is not circular, it's a rectangular concrete box. And so put in concrete box, the span of which is 1,500 millimeters. The rise is 1,500 millimeters. And we're not going to make any changes to the embedment depth, but I think that it did say the roughness of this concrete was 0.013. So we're going to have to change that Manning's N from 0.012 to 0.013. It's a little bit rougher. And we'll leave all of the inlet configuration as just the default kind of middle of the road typical values. All right, inlet station. We don't have station set up, but we know that the culvert is 40 meters long. That was given here in the problem statement. The length of the culvert is 40 meters. So we could call this like station 0 and call the outlet station 40. And from that, it's going to know the length of the culvert is 40 meters. So inlet station 0, outlet station 40. Okay, so that is just defined the length of the culvert. And then when we tell it the inlet elevation and the outlet elevation, that's what defines the culvert slope. So inlet elevation 100, outlet elevation 99.72. So just to re-emphasize this point, we weren't given elevations. We had to synthesize some elevations to put into the program so that from the elevations and the culvert stations, it would know how long it is and what slope the culvert's at. You'll probably have to do the same thing in the project. I don't think in the projects I've necessarily defined elevations, but you'll just have to say, well, let's just have this one control point be our culvert inlet, and then all of the other elevations are relative to this one place that we're going to say, let's make this 100, and then everything else is based off that. All right, you can see it's computed the culvert slope to be 0.007, which that confirms what we know from the problem statement, that we just want this culvert laid out on the bottom of the channel, and the channel has a 0.7% slope as well. So click Analyze Crossing, and let's see what this summary table tells us. It says we want to find out when the headwater is 2 meters, what's the flow rate? So when the headwater elevation is 2.1 meters, then the total discharge is 6, and none of that is going over the roadway. So between 101.8, which is 5 cubic meters per second, and 102.1, so that's not, we can't say between 5 and 6. That's not precise enough for us. But what we can do is we can have the program do its simulation between 5 and 6 instead of from 0 to 10. Like you'll remember we told it the minimum flow and the maximum flow to include in its simulation. So it's going from 0 to 10 because we told it do it from 0 to 10. What we'll do next, we'll say focus in on 5 cubic meters per second as the minimum flow rate, 6 cubic meters per second as the maximum, and then that'll give us a lot more precision in elevations to really hone in on what's happening at 2 meters. By the way, there are a variety of other reports it can generate besides this summary. And I don't usually bother with them because you can just get the information you need from here, but you can export reports. Let's just take a look at what one of those looks like. HY8 report. Okay, so I think it's just saved this HY8 report. Maybe. There it is. It's opening it, seems like. Okay, so this is that table that says headwater elevation versus how much is it going through the culvert versus how much overtopping there is. Oh, that's the only thing in the report? That's not as maximalist as I was expecting, because there are other reports that we can get from it, but culvert summary table. So same stuff, discharge, elevation, but then this will start to tell us the flow type. Remember from last time there was inlet control, outlet control, and different types of inlet and outlet control, like what's the limiting factor of driving flow through the culvert. And the flow type will tell you, if you were going to use manually one of those equations or nomographs, which one is governing at a certain depth and flow rate. So, feel free to play around with these different displays, but the crossing summary table will give us the answers that we need. All right, so let me show you what I mean, though. If we go back into the culvert, and instead of going from 0 to 10, let's go from 5 as the minimum flow and list 6 cubic meters per second as both the design and the maximum. Okay, now analyze the crossing again, and what it's doing is it's starting with 5 cubic meters per second. It's telling us what's the headwater elevation with that. So we've just got like a lot more of the data points in the vicinity of what we're interested in. And if you'll notice, here it's saying 102.01. So now we're able to say with a lot more precision what is the flow rate associated with the headwater depth of 2 meters. It's about 5.7. So like if we wanted to be really lunatics about this, what we could do now is say, well, let's do a simulation from 5.6 to 5.8. Okay, so if we have it as the minimum being 5.6 and the maximum being 5.8, and have it analyze the crossing again, here it is exactly 1.02 headwater elevation is associated with the discharge of 5.68 cubic meters per second. All right, so we've answered part A. So Q equals 5.68 cubic meters per second. And this was through a 1.5 meter by 1.5 meter culvert. So there's about half a meter of water above the crown, meaning the top of the concrete box culvert, but it's not overtopping at that level. Looks like the tailwater, So we've got a nice wide channel downstream of this culvert. It looks like the outlet's not submerged. Although the inlet is submerged, the outlet is not. Anybody know why it's showing this as trapezoidal on top? It's because the culvert is 40 meters long, and I said that the width of the roadway, I think I said that was, what, like 8 meters? So it's just assuming that the roadway is like centered on top of the culvert. And this is a pretty typical thing, that if you do have a culvert, you may have like soil beneath the road, and so you can't have soil with a vertical slope. You'd maybe have to have a tapered slope leading up to that. So typically culverts will be longer than the width of the roadway. So that's why the example that we were working through on Monday, it was just like a vertical face, but here the roadway width is quite a bit less than the culvert length. So that's why we've got that trapezoidal shape on top. Okay, part B was asking, what is the rectangular channel width that will cause the tailwater depth to be 2 meters? So right now, let's take a look at the tailwater condition. If we go to this rating curve, so right now the bottom width is 5 meters, and part B is asking, how narrow could we make the channel that would force the tailwater up to a depth of 2 meters for a flow rate of 5.68 cubic meters per second? Okay, so when we've got the 5.68, the tailwater depth is only 0.896 meters. So let's just write some of this down. Here right now for part B, for B equals 5 meters and Q equals 5.68 cubic meters per second, then the tailwater depth is 896 meters. So what if, it's expensive to excavate. It's expensive to buy real estate. If this was like an irrigation canal, which they have a lot of those out west, sometimes they wind their way through residential neighborhoods, even where you're having to buy right-of-way, where you're impinging on resident landowners' property to put some sort of an irrigation canal. So why make it 5 meters wide if the water depth is going to be so shallow, 0.896 meters? So this is kind of just like an optimization process, asking how narrow can we make the channel to force the water up to 2 meters of depth? Because right now, for the flow rate we're interested in, this flow rate of 5.68 cubic meters per second, the tailwater depth is much lower than this 2 meter limit. All right, so how we would do that, this is actually a pretty simple process. 5 meters is too wide. What about 4 meters? We'll view. Okay, at 4 meters width and 5.68 cubic meters per second, now the depth in the tailwater is 1.07. So that's not yet up to 2, so we can make it narrower. What if we make the channel 3 meters wide? View the tailwater report. 5.68, 1.4. Okay? Still not as narrow as we could be. What about a width of 2 meters? View the report. 5.68, depth 2.18. So we've gone a little too far. Now this is one of those things where I mentioned on Monday, I wish we had goal seek. We don't. We have to do this the old-fashioned way. So 2.1, view. 5.68, 2.059. We're getting awfully close. We just have to make the channel a little bit wider, and I think we're going to be there. So maybe 2.15. And we'll see. We won't do it in millimeter increments. But assuming that they could make it 2.15, the depth is 2.003. So we'll say that's close enough. So the answer to part B is we could make B equal to 2.15 meters for the flow rate of 5.68 and looking for a target tailwater depth of 2 meters. Okay, so any questions about this first analysis problem that we've just worked through together? What I'd like to do with our remaining 20 minutes is I'm going to stop talking and give you time to work on this either on your own or with a classmate. Just for this next problem, I'm asking you to consider a culvert which is 40 meters long and has a top width of 40 meters. The height from the bottom of the channel to the roadway surface, 8 meters there. We want to carry 10 cubic meters per second. 10 cubic meters per second. It's a trapezoidal channel, so the bottom width is 3, 1-to-1 side slopes. You can see the end value. Design a culvert. So I haven't told you if it needs to be a concrete box, a concrete circular pipe. It could be galvanized steel. Just pick something so that the maximum headwater is 7 meters for the 10 cubic meters per second. And then for part B, make the culvert a little bit smaller than it was, because in part B, when you make it a little bit smaller, what we're going to have is 1 cubic meter per second of the 10 is allowed to overtop. And so how small should the culvert be to allow 1 cubic meter per second of overtopping and 9 cubic meters per second going through the culvert? And by the way, just looking back at the report, when we are doing the analyze crossing, one of the columns it tells you how much is going through the culvert, and then the roadway discharge is the amount of flow that occurs through overtopping. All right. So I'm going to pause from talking, give you some time to put this in, play around with iteration, make it as small as possible, and then I'll fire up mine and do the same thing towards the end and just see if we come up with some of the same shapes and sizes. Let me just talk you through a couple of points that I think are important. One is the crest length. So the roadway station, that doesn't affect your hydraulic calculations, but the crest elevation obviously does. Like if you put that too low, then it's going to begin overtopping prematurely. But the crest length, I said 21 meters. And the way that I estimated that is, remember here in this front view, let's say we've got a circular concrete pipe. The water level is rising, and the problem statement said that the elevation difference between the bottom of the channel and the roadway surface is 8 meters. So if we take that to this front view, 8 meters is where the road is. So here's the roadway surface, and it's a trapezoidal channel. So how long is that roadway surface over the channel part of it? So 3 meters wide, and then it's got 1-to-1 side slopes, right? The problem statement said it's 1-to-1. So every unit of depth also is giving us a unit of width on the top. So that top width is going to be 8 meters on the left side, 5 meters in the center, and then 8 meters on the other side. So that's 21 meters total. So that's why here for crest length, I think it's a good estimate for us to say that if the water does begin to overtop, like the water level is rising and rising, then it starts flowing over the top of the road with the width of 21 meters. And then the width of the culvert would depend on how many lanes we have, and it's maybe a little bit less important to know the depth of the flow over the roadway than the crest length is. But okay, so just as a starting point, I suggested let's see what happens with a 1,500 millimeter concrete culvert. And I put in all the same culvert invert characteristics that we had on the previous problem. Like I said, let's have the inlet elevation be 100, the outlet elevation be 99.72. So tell me, is my culvert too big or too small right now? Is 1,500 millimeters oversized or undersized if the criteria is the headwater is allowed to rise up to a depth of 7 meters? So who can diagnose? Maybe it's hard to see because that's kind of small. It's oversized. And what's the indication of that?
Your design flow is less than 107.
So let's look at what elevation, like when we get up to a 105, I'm carrying the 10 cubic meters per second. So it's allowed to get up to 107 for 10 cubic meters per second. So I can make my culvert smaller. So right now, that's correct. It's oversized. So if it was going to be built in 100 millimeter increments, I don't know what's commercially available, but let's say 1,400 would be my next smallest size available to analyze. So now, at what elevation is it for 10 cubic meters per second? 106.59. So we're getting closer to that upper threshold of 7 meters of depth. I don't know if I'm going to be able to step it down one more. Probably if I do, it's going to bust through that upper limit. So let's just take a look. If I downsized it to 1,300 and analyze. Now, 10 cubic meters per second is associated with 8, a depth of 8.05. So we see that it is going to start to overtop a little bit. So I think the answer from the design perspective is if it's concrete and if these are available in 100 millimeter increments, then the minimum size that would be allowable would be 1,400 millimeters. Because at 1,400, we were within that upper limit that's allowed of 7 meters of headwater depth. So did anybody make a different geometry aside from circular? Anybody do a box culvert? Or I guess if you had a circular but it's corrugated steel, it's going to be a completely different thing. Or like high density polyethylene, you're going to have different characteristics there as well. It'll generally be within the same range of cross-sectional area. But that's kind of the design process I envision you going through for the project. You know, in the project I've given you some limits on how much overtopping flow there can be. And so you just go through the constantly making a little bit smaller and seeing how high does the water get for a certain flow rate. Like in part 2 here, it asks, design a culvert that allows up to 1 cubic meter per second of overtopping. So now that means I can maybe go even smaller. What does it do at 1200? Analyze crossing. So at 1200 millimeters, I would have 8.2 cubic meters per second going through the culvert, and the rest of it is going through the roadway, overtopping. So that's too small. So maybe I'd have to make it 1300 and then analyze. So 1300 would be as small as I could make it to have no more than 1 cubic meter per second of overtopping. Of course, maybe I could make it custom sized. Maybe if I was able to do 1250 or some custom size to the exact, actually 1250 is pretty near exact. If you look, of the 10 cubic meters per second, 8.98 is going through the culvert and 1.02 is going over the top of the roadway. So that would just about exactly match, maybe a little too much overtopping. So if I made it just a couple of millimeters wider, then that would convey more of the flow and have less of the overtopping. So 150, we're out of time. Hopefully that hands-on practice was useful to just get you thinking in 3 dimensions when it comes to culverts and understanding the process of iterative assessment through HY8. And that's what you're going to need to do for the project, which is due on Monday. So let me know if you have any questions on HY8 or on the WMS part of it, and I'll see you in class on Friday.